Good evening, everybody. Welcome, everyone, to our live deep sky tour. My name is Stephen Hummel. I'm going to be your host tonight for this program. Uh, I will be showing you a little bit around the sky with this 16-inch telescope here behind me, showing you some live views of some deep sky objects. And tonight I have an array of different objects for you to see, including some highlights of what we would call the summer sky around this time of year, as well as some more obscure and odd objects that are kind of overlooked, in my opinion, in the sky. But I think we have a pretty good show for you. Before I get started, I do want to note that if you have any questions for me or other astronomers, you are free to use the live chat and ask your questions there. We have a team of moderators standing by to help answer some questions, and they will also be forwarding some of those questions to me at the end of the program. If you're interested in learning more about the equipment I'm using, there is in the description some specifics, the cameras and such. Tonight I'm going to be using a monochrome camera, which means it's black and white. It's a black and white camera, and as opposed to a color camera. And the purpose of that is that monochrome cameras are very popular in astronomy because they're very sensitive. They're far more sensitive than the equivalent color camera ever could be. Also, it happens that when you're actually viewing things at night in person with an eyepiece on a telescope, you don't actually see color anyway. So, in one sense, the views then are a little closer to what they would actually look like to your own eye, although they actually do have color. Many of the objects we'll show tonight do have color. Um, but yeah, we'll be using the monochrome camera. We are going to be looking at some really, really faint things, pushing our equipment to the very limit of what it's capable of tonight. So we're going to benefit from that for sure. Um, again, we're located at McDonald Observatory, and McDonald Observatory is in far west Texas. We've gotten a lot of rain lately. It's greened up nicely. Hasn't been this green in years. This is actually an older picture, but it's pretty close to what it looks like right now. I am located at the Visitor Center, which is down. I'm sorry, that's the wrong dome. Let me get the correct one. It is. Oh, okay. That's not it. There we go. That's the picture I want. I'm located at the Visitor Center, the Franklin Bash Visitor Center, and we have again, the 16-inch telescope pictured here. It's the same one that's behind me in the webcam. And this telescope is typically used for outreach and for folks like you to enjoy. And we do hope you find the time to visit us in person. We are open to the public. We do require reservations to attend our programs, our view with our telescopes, either virtually or in the future, probably in the fall, the traditional way with eyepieces again as well, as long as conditions permit. Okay, but we have, again, really great weather tonight. This is a live view of the entire sky. It's almost totally dark. There's still a little bit of twilight left. We're just waiting for that to kind of fade out before we really get started viewing some of these fainter objects. At this time of year, the sun sets very late, a little after 9 o'clock, and it really doesn't get dark until about 10:15 local time. We're on Central Time, but really we probably should be on Mountain Time, given how far west we are. But nice temperatures, really pleasant. Just all around great night. We've had a lot of rain lately, as I noted earlier, and so it's been cloudy a lot. So I'm really thankful that it is so clear tonight, because lately it hasn't really been. All right, but our first object for tonight, the first object we're going to take a look at, is called NGC 4565, and it's located in an area of the sky that's actually very full of galaxies, and what we call sort of near the Virgo cluster, which is that big group of little red specks there. But it's actually not in that constellation. It's in the constellation of Coma Berenices, or Berenice's Hare. And this is sort of in the western half of the sky. If I zoom out and look at this map of the entire sky, you can notice a very stark difference between the two sides. This line going up and down the middle roughly marks the kind of middle part of the sky. Don't pay too much attention to that because it's really more for telescope operation than what you should care about. But basically, this is straight up and straight down. Let me recenter it there. So again, our first target's over here. You can see a little bit of the Milky Way starting to come up. It's not quite dark enough to see that on the live view very well in the lower left corner. That's the live sky, which matches what we're seeing here in the sort of the map. But we generally call this area of the sky, where there's a lot of interesting stuff, astronomers tend to call that the zone of avoidance, which is kind of interesting, maybe a little counterintuitive. Where there's a lot of interesting stuff to look at, we call it the zone of avoidance. Well, that really stems from radio astronomers and astronomers who study other galaxies aside from the Milky Way. Because in this direction, over where we have sort of the Milky Way, we have so many foreground stars and gas and dust that blocks the view of further objects. There's too much stuff in the foreground. Whereas all these little red specks here, these are some of the brighter galaxies in the sky. There's actually far more than that, but there's some of the more interesting ones noted here on this wider view of the sky. And you can see that there's a lot more over here. And part of that is because there just are more there, but part of that is also because there's less stuff in the way, so we have a clear view in this direction. So the first couple objects we're going to look at are galaxies. And again, this first galaxy is called NGC 4565, also known as the Needle Galaxy. And let's take a look at that live view right now. There it is. This is the live view from the telescope behind me. Yeah, you can definitely see it is very thin, kind of needle-like, with a very bright core. Now keep in mind, it's still not even 100% dark yet, but we're still able to kind of bring this out. As far as galaxies go, it is relatively close and relatively bright. This is a favorite among amateur astronomers and professional astronomers alike. It's a really popular target to look at visually the traditional way, as well as take pictures of, like we're doing tonight. And it's actually been the sort of first object several major telescopes in the world looked at when they were first built, or their first light target, just because it's so photogenic and it's so bright and interesting and detailed, and it really shines in a large telescope. That is a big bright satellite, which has just happened to pass through our field of view there. We see a lot of satellites at this time of the evening, just after sunset, right before it gets truly dark, because those satellites are high enough up that they are still reflecting a little bit of sunlight off of their bodies and their solar panels. So we tend to see a lot of satellites around this time, and then just before sunrise. We don't see as many satellites, especially not as bright as that, around midnight, for example, because the angle of the sun isn't right. So hopefully that'll go away, or at least be averaged out. I should add that I'm taking multiple exposures. So I'm taking 30-second exposures, and then I'm combining them together, averaging together to create a deeper and cleaner image. It's a technique called stacking. So the image you're seeing is a live stack, basically, or I'm adding more images every 30 seconds. You can just see it just refresh there. It gets a little better. So that satellite was so bright that it's going to take a while for that to be averaged out. But so it's going to remain there for a while. Yeah, again, the Needle Galaxy 4565, the new general catalog. This is a relatively easy telescope target to find for yourself. You do have to kind of do some star hopping and use some other brighter stars to kind of figure out where it is. But it is something you can see under dark skies with an amateur telescope pretty easily. In a large telescope, it's really amazing. But it is indeed a galaxy, meaning it is a vast sort of city of stars, usually on the orders of billions to hundreds of billions when we're talking about galaxies in general. In this case, it's probably around there, probably tens of or hundreds of billions of stars. And it is roughly 42 million light years away. So 42 million light years. That's the distance or the light travel time to reach us. So we're seeing it as it was 42 million years ago. So again, a light year, if you're not familiar, is the same as a regular year, but with fewer calories. I'm kidding. No, that's a pretty lame joke. But no, a light year is a unit of distance. It's the distance light travels in Earth year, and that is 5.88 trillion miles. So that's a hefty distance, and or one light year. So 42 million years for this light to reach us. So 42 million times 5.88 trillion. There's our answer in miles. It's roughly 100,000 light years across, from edge to edge. And you can see it's a lot thicker in the middle. It has what we call a galactic bulge, essentially a thicker portion near the center, and that is roughly 20 or to 15,000 light years thick if you count the full extent of it. But generally, this galaxy is really thin. Now, this galaxy is a spiral galaxy, even though we don't see the spiral shape. We know this because, well, of some fancy tools we have to analyze galaxies, but it's difficult to tell. And in general, when you see a galaxy like this, it is probably a good bet that it is a spiral galaxy, because spiral galaxies tend to be very thin. We can't appreciate that spiral shape because we're viewing it almost exactly edge on. So if we were to view it from a different angle, we would see its spiral shape very well. And we classify galaxies in many different ways, but the general way we classify them is on this chart called the Hubble-de diagram. And de Vaucouleurs was an astronomer here at McDonald Observatory, and he kind of added to what we call the Hubble tuning fork and refined it. But there's some debate about exactly what kind NGC 4565 is. It's probably an intermediate spiral. It has a little bit of a bar structure, but it's not super obvious, and it's difficult to tell how tightly wound those spiral arms are. So where exactly it falls, we're not sure, but it's probably somewhere in an intermediate or kind of barred spiral part of the chart, and those two branches, which is roughly about the same as our galaxy, the Milky Way. And our galaxy also has a line of dust and gas within it. And that's what you kind of see kind of dividing the galaxy along its edge. You can clearly see that when you look at the center, there's a dark line kind of in front of it. And that is mostly dust, by which I mean literal kind of dust, like sort of similar to what we have here on Earth, but also things like carbon and hydrogen and iron and silicon and even sometimes odder molecules like even some simple sugars can be found in clouds like that. So this is a pretty big galaxy on the sky and nicely fills our field of view here. But here is a view previously taken with a slightly wider, slightly bigger camera chip, so it fills more of the field of view, but the same telescope. So I took this previously, but here displayed in color. You can see it's quite colorful. But let's take an even deeper look at just one little slice with the Hubble Space Telescope. And the Hubble Space Telescope is very powerful. It has great resolution. But it has a relatively small field of view. Actually, a very small field of view by modern standards. So it can't get the whole thing at once, but it can get incredible detail on one specific spot. And you can see those lines of dust a little better there. And you can definitely see more of the color. You can see there's some blues in there. And if we go back to the wider one, we can see the core is slightly yellow. So the color tells you a little bit about the star. Generally speaking, if you see blue stars, they're very hot, they're a bit more massive, and they are relatively young. So they formed relatively recently in the history of that galaxy, usually millions or billions, or not even billions of years ago, usually hundreds of millions at the most. Whereas some of the older stars tend to be lower mass, and they tend to be kind of more yellowish. And you find more of those in the middle, in the bulge. and they're not as bright, but they live longer. So all the big blue stars eventually die off, and what's left behind are sort of the yellower ones, the fainter ones. And they tend to kind of be concentrated more, obviously, in the older sections of the galaxy. But when we look at this galaxy, we see that line of dust and gas. And in our own galaxy, the Milky Way, which we live in, when we look up in the sky, we see a similar thing. We see that line of dust and gas in the Milky Way. And the Milky Way probably would resemble NGC 4565 if viewed from the outside. It's not a perfect match. There are definitely some differences, but it would look more similar than different. But because we're inside of it, we see this sort of line of dust and gas kind of much more obviously, and it's kind of spread around a little more, and we can see the stars and stuff above and below it as well. All right, now it's almost as dark as it's going to get. So we're going to move on to the next target. Let me see if there are any questions about that galaxy or anything else before I head over there. Again, remember you can send your questions into the chat at any time, and the moderators will send them to me. But next up, we are going to go to one of my favorite objects in the sky, and one of the most unusual at that too, called Hoag's object. Usually in astronomy, we refer to things like the so-and-so galaxy or the such-and-such cluster or nebula, but it's pretty rare that we just say the object. Like that's pretty nondescript, and that's because at first astronomers weren't really sure what it was. So that's what we're going to do next. We're going to go to this odd little object. It is actually a galaxy. Hoag's object is a galaxy. We know that now. But I'm going to talk a little bit more about that. So I've moved the telescope to PGC 54559. That's the catalog name for Hoag's object. You got to dig pretty deep, to see that one. But Rebecca Riley asked, what causes the different shapes of galaxies? Well, galaxies come in a large variety of shapes. And generally speaking, most galaxies, if you don't interrupt them, you don't mess them up at all, they will form spiral shapes over time due to gravity and basically just gravity and time and sort of waves of material flowing through them. But galaxies can come in other shapes, including sort of just big round spheres, what we call elliptical galaxies, and those you tend to get those when you merge galaxies together, or one galaxy just keeps getting merged and merged and merged again with other smaller galaxies into one big kind of egg-shaped blob, and all the structure is lost. But the specifics behind why some galaxies are very tightly wound spirals and why very loose, some are more loose, and why some have bars, actually get pretty complicated. And it's an active area of research that we definitely don't completely understand. And this next object is really going to highlight some of the holes in our understanding of the shapes of galaxies and how they form that way. But again, this galaxy we're going to look at, Hoag's object, is one of the most unusual objects in the entire sky, one of the least understood. And it's also right on the cusp of what I would say this telescope could actually observe in a program like this. It is really, really faint. Okay, so the last object I showed you was a particularly bright and close galaxy. This next galaxy is 600 million light years away. It took 600 million years for its light to reach us. Just let that sink in. Like, the Earth 600 million years ago was just a radically different thing. I mean, the continents would have been in completely different positions. Pangaea, the big supercontinent, was like 300 million years ago. The dinosaurs were killed by the asteroid about 66 million years ago. This is 600 million years for the light to reach us. So the galaxy may be completely different now. We don't know. It's a big chunk of time. Even for a galaxy, that's a significant chunk of time. But it is, because it's so far away, it is incredibly faint. So just keep that in mind as I show you this. It's going to take a little bit for it to really start to come out and be obvious. It's just above the threshold of visibility right now. So again, it's right in the middle. Okay, I know it's not really quite obvious, but let's put this pointer right there. It is kind of faint. If you were to look at this spot in the sky with your own kind of telescope, even a pretty big amateur telescope, maybe 20 or 30 inches across, you would see almost practically nothing where that arrow is pointed. You might see a little bit of the center there, that little brighter speck. So all of these objects around the pointer, they're almost all of them are stars in our own galaxy. And so they're in the foreground. They're much closer, and we can actually resolve them as individual stars. Right where that pointer is, that little kind of fuzzy spot, is in fact the core, the elliptical core of this very distant galaxy. And you can see that there's a very faint ring around it. This is an incredibly rare type of galaxy called a ring type galaxy. And if we go back to our chart, well, we have ellipticals, we have spirals and barred spirals, intermediate spirals, and if a galaxy doesn't fit in any of those, typically astronomers would then call it an irregular galaxy. But if you look at most irregular galaxies, they are kind of just, well, irregular. They're amorphous blobs. They don't really have any obvious structure. Things are kind of just organized any which way with no obvious sort of grander structure to it. If there is, it's very, very loose. Whereas this galaxy does have structure. It has a ring shape, so it doesn't really fit into any of those categories. But let's take a different look at it. I'm gonna try to bring out more contrast to this. It's gonna be a little tough, but you know, you can kind of start to see it. Let me reset it there. I'm just adjusting the settings to kind of make it more obvious. But you can definitely see that there is sort of a ring shape in there. A lot of people, a lot of amateur astronomers wouldn't even consider this target something that is possible to see with an amateur telescope. You really absolutely have to have dark skies to see just that faint little ring. It's thousands of times fainter than the faintest thing you can see without a telescope under dark skies. And it's really tiny, too. So let's take a look then at a previously taken image. Same telescope. This is a 10-hour exposure and with filters to create the color. But same camera, same telescope. And you can definitely see that ring shape there very well. You can see that there's a brighter sort of center, and then around it is a fainter ring. And there's a very clear gap between the center and the ring. That's, I think, a pretty good picture. I haven't seen many amateur pictures of this target at all. There's very few people have even attempted it because it is so faint and so small. But the Hubble Space Telescope has taken a nice hard look at it. This is actually a relatively old picture. It's almost 20 years old now. Hubble was launched in 1990. It's an aging telescope, but you may have heard that Hubble is currently non-operational due to most likely a computer malfunction. And they haven't fixed it yet, but they are actively trying to. I really hope they can, because there's really nothing quite like it with its capabilities, and there won't be for quite some time. But this is the same object with the Hubble, and what an odd object. Like, you can see that the center is kind of yellowish, and you can see that the ring is a little bit blue. So kind of look at the previous galaxy. We have a collection of older stars, lower mass stars in the middle, and younger, brighter, bluer stars in the outer portion. But there's just a big gap between the two. Well, the question then is, how did it form? How did it get this structure? Why isn't it a spiral like all the other galaxies? Well, there are a few other ring galaxies. Hoag's object is not the only ring galaxy. There are a few others. Here's an example. You can kind of see it's got a ring shape to it. That one too. It's got a slightly ring-like shape, but not symmetrical. It's a really beautiful example called the Cartwheel Galaxy. Again, these are all Hubble shots. And another one, it's amazing structures here, but notice that they're all asymmetrical. None of these are quite as perfectly round and well-formed and smooth and even as Hoag's object is. It's just, a perfect circle. There really isn't any other galaxy like that. And Arthur Hoag, the astronomer who first discovered this in 1950, when he first saw this little round object, he thought it could be a planetary nebula, an entirely different kind of object, and we're going to see an example of a planetary nebula in a couple of targets later on in the program. You'll see why he thought that, because to the untrained eye, it looks more like that than a galaxy. But then he realized it probably was a galaxy, and then he came up with, a few different explanations. And astronomers generally have, there are a few different attempts to try to explain it. The first attempt was to say that it is an example of gravitational lensing. And this was disproven, but the idea was that when we see this in other objects, when you have a very massive object and something behind it, way off in the distance, the gravity from the massive object can distort and bend the light from the object behind it, and can actually act as a lens and distort it even into ring shapes. There's lots of examples of that. They're called Einstein rings, and that's really neat. But when we took a look at it in higher resolution, like I can kind of see with our live view here, as well as with the Hubble view, which I'll bring back up, that's not the case because there's way too much structure in the ring. We're definitely seeing stars and gas and things in the ring. It's not being distorted. It's not a lensed effect, so that can't be it. So there's two other attempts to explain it. One is that it is the result of a merger with another galaxy. And that's the case with all of the other ring-type galaxies I showed. There are multiple galaxies, or at least two, and they are gravitationally interacting with each other, in the process distorting the galaxy and ultimately creating that ring shape. So basically, other galaxies triggering that ring shape or causing it to form either indirectly or over time. But the other explanation is that it just formed by itself. And if we look at all of the other ring-type galaxies, they all are the results generally of merging or interactions with other galaxies. So that's a good indication that Hoag's object probably is the same, but we have no evidence of that with this particular object. We have no evidence of any other galaxies nearby. There's no sign of any nearby galaxies, whereas if we look at the others, very clearly, there's one galaxy and another one, and here's another galaxy of some others nearby, and especially with the Cartwheel Galaxy, there's some other little galaxies nearby, but not with Hoag's object, not with this galaxy. And detailed studies have looked for any traces of fragments, like maybe there was in the past and they've merged together, but there should still be something there, and we find nothing. No evidence of another nearby galaxy. Okay, so then maybe this formed over time just by itself. If the galaxy sat there long enough, maybe it formed it by itself. But, simulations don't quite work to explain that, and there's not a lot of evidence that that happened organically. Well, at least our models can't really make sense of that. And one thing to note about Hoag's object, as opposed to, say, the previous galaxy we looked at, which was a disk with a little bulge in the middle, is that in the case of this object, the center is a sphere, whereas the ring is, kind of a donut shape, a thin donut shape. And it's very difficult to explain how that kind of organically evolved over time. So there's some debate. Both explanations, all the explanations have some problem. If you ask me, I think it probably is the result of a merger, given that all of the other ring-type galaxies we know of were the results of mergers too, and maybe we just don't have that sensitive enough equipment to find the evidence, and it was probably many billions of years ago, and so that evidence has sort of been erased over time, flung out, or merged with the galaxy. But yeah, it is still remarkable. It's still very poorly understood. Rebecca Raleigh asks again, why are ring galaxies rarer than spiral galaxies? Under what gravitational conditions do ring galaxies form? Spiral galaxies form. The spiral shapes are dynamic. They are not stationary, and they actually change a bit over time. Whereas ring galaxies, some of them seem similar. They're only maybe a phase in the galaxy overall, and some of them seem to be kind of permanent. They've sort of settled into a stable structure. But getting to that condition requires unique conditions, which again we're not actually entirely sure how that happens. But almost all galaxies are spirals or big blobby ellipticals or just irregular blobs with no obvious structure at all. And generally speaking, if you leave a galaxy by itself, the modern understanding is that over time it will develop a spiral structure. Just if it's not interacting with anything else, just over time through gravity. I go a little more into depth on the structure and how the spirals work in a previous live stream. You could rewatch from last year. Actually a 3-part series on galaxies and dark matter and dark energy. So you can go watch some of those recorded ones. Miss Karen asks, how are we measuring the distance of these galaxies from us? Generally, when we're talking about something this far away, at 600 million light years, we are doing that via the redshift. It's another topic I talk more about in a previous live stream, but the idea is the universe is expanding at a roughly known rate, and as the universe expands, the further the object is, the faster it appears to move away from us. So if we measure how fast it moves away from us, we can work backwards and get a rough idea of the distance. It's not perfect, but we can ballpark it. So 600 million light years for this, plus or minus several tens of millions of light years. So depending on who you ask. Okay, our next object is a lot brighter, but I'm going to go back to the live view one more time. And see if I can adjust the contrast, bring it out just a little bit more there for you. Again, really faint, really difficult one. Can just barely make it out. I kind of overdid it there. But yeah, amazing. I think that we could actually live stream something like that. It's again right on the cusp of what's technologically possible with this equipment. You can also begin to see that there are a few other background galaxies. For example, there's another one, another little pair over here, but they're pretty far. They're not actually the same distance. They're actually a very different distance. I'm not sure if they're closer or further, but they're not related to Hoag's object. But again, all right, next target, a lot brighter. You can see the Milky Ways come out nicely there. Still have very nice clear skies. But the next target is a favorite of the summer sky. It's called Messier 13 or M13, also known as the Great Cluster in Hercules, in the constellation of Hercules. So you can see the telescope moving behind me. And let's see here. Bring this camera back up. I'm going to start moving the dome to spin around to that part of the sky. So M13 is one of the brightest globular clusters in the sky, which are kind of giant balls of stars, globs of stars. And it is actually visible with the naked eye under dark conditions. If you're dark adapted and you know where to look, you can spot it. I'm looking up in the sky and I can see it right now. It's pretty tough, but you can see it without any optical aids at all. And that's definitely not the case with Hoag's object, which is almost invisible with all but the largest telescopes in the world if you were to view it with an eyepiece, without the aid of a sensitive camera like we're using tonight. All right, so again, M13 it is an example of a globular cluster, and it is located roughly 22,000 light years away. So a lot closer, right? The first object, the Needle Galaxy, was 42 million light years. Hoag's object was 600 million light years. This is 22,000, so a lot closer. And everything else tonight, too, is also going to be a lot closer than those previous galaxies. It is basically part of the Milky Way, but not quite. It is located above the disk of our galaxy, the Milky Way. This is kind of a artist's interpretation of our galaxy here. And you can see that it is located slightly above. The sun, our solar system, is located kind of within the disk there, basically in what we call the thin disk, basically right in the middle. We're about 25,000 light years from the center of it, which is there. You can see the bulge around the center, and M13 is 22,000 light years away from us, so it's roughly, 17 or 18,000 light years above the disk. And all of these clusters like M13, which are all marked on this map, they all are in orbit around the center, but they are not in orbit along with everything else. They're kind of going every which way around the center, whereas all the stars and gas and dust in the Milky Way is kind of orbiting along inside that plane. These globular clusters, they're kind of all over the place. So they're part of the Milky Way, but they're kind of in the rural outskirts in a sense. They're not quite in line with everything else. All right, so we're going to pull up the live view here in just a second. Just taking that shot. All right. All right, and let's see here. Here we go. Here is the live view. I'm going to get rid of that pointer there. Don't need that anymore. All right, so M13, or the Great Cluster in Hercules, whatever you'd like to call it, is, again, an enormous ball of stars. It contains several 100,000 stars, and it is roughly 145 light years across from side to side in diameter. So it's big. For reference, from the Sun to the next closest star, Proxima Centauri, is 4.2 light years. The Sun to the next star. And that same distance, if you're in the middle of this globular cluster, you'd have perhaps many dozens of stars in that same area. So M13 is very dense. There's a lot of stars packed into a relatively small space. And generally speaking, these are older stars because globular clusters in general are very old, many billions of years old. In this case, about 11.85 billion years old, which is, a bit is much older than the Sun, which is about 4.5 billion years old. But most of these stars are lower mass. They're mostly much fainter than the Sun. There are some exceptions. There are some brighter ones in there too, and those are probably formed from some of those smaller stars either merging or stealing material from their neighbors, and thus gaining mass by stealing it from others, which actually makes them a little brighter and a little bluer too. But here's a color view of M13. And you can see that there are some yellow or redder stars as well as some bluer ones in there. Those very bright redder stars are stars that are kind of nearing the ends of their lives. Some of them are red giant stars, which are running low on fuel and expanding and puffing up their outer layers and cooling off in the process, thus making them a little bit more red. Whereas the younger, hotter stars shine a little more blue because they're a little bit hotter and they haven't puffed up yet. Whereas kind of in the background too are many smaller, fainter, just yellower stars that just never really never really gained their temperature, and they probably still have many billions of years of life left in them. But a very dense cluster, just exceptionally dense. Really a fantastic target for an amateur telescope or even binoculars. Again, it's not too hard to find. You can just barely see this with the naked eye. I mean, you kind of know. Again, you have to know where to look, and you have to be very dark adapted. But it is totally possible to see this without any telescope at all if it's a moonless night under dark skies. You're dark adapted. All right. Again, that's M13, and we're going to move on now to our next target, which is one of the more obscure ones. Again, we're doing the highlights of the sky, then some obscure ones too. Don't want to let them, we want to share the spotlight a little bit, share the attention. So the next object is NGC 6765. And it is an example of a planetary nebula. I mentioned those earlier. And planetary nebulae are kind of the end stages of stars, like the sun, or a little bit larger. And it is in the constellation of Lyra, the harp. There's a very, very famous planetary nebula in this constellation that is very popular among amateur astronomers called the Ring Nebula. And it's located right around here. Ring Nebula is over here, also known as M57. And this is a lot fainter, but it's located kind of just below it. NGC 6765, once again. This one doesn't really have a good nickname. I'm going to put forth the nickname the Jack Nebula. By Jack, I mean like the playing jacks, like marbles and jacks. You'll see why in a minute. Kind of looks, I think, a little bit like that. And again, that's a pretty faint target. So give it a minute before it really starts to come out. Let's see here. Gonna take some longer exposures on it. First, I'm gonna adjust the dome a tiny bit as well. Don't have to very much in this case. Alrighty, so let's see what we've got here. Almost have this picture loaded up for you. Alright, so we have a faint little smudge in there, which you can see in there. So planetary nebulae, again, how they form is basically in the end stages of a typical star, by which I mean less than 8 or so times the mass of the sun, or really, in most cases, less than 5 or so. When a typical star dies, when it runs out of fuel, it puffs up, blows off its outer layers into space, and what's left behind is just the core, what we call a white dwarf. And the energy and heat from that white dwarf pushes material outwards, which energizes some of the material previously ejected and makes it glow. And I have a little animation of that. So again, the star expands, puffs off its outer layers. The core of the star collapsed down into what we call a white dwarf, which is roughly the size of the Earth, which is very small for a star. It's about a factor of 1,000,000 compressed down. And the heat and energy of that kind of core, the remnant of the star, basically an ember, energizes the gas around it and makes it fluoresce. Often very interesting colors, shades of green and red and other colors too. So that is the kind of thing we're seeing. And planetary nebulae come in all kinds of interesting shapes and sizes. But most of the time, they look kind of like rings or something like that. But what we see in here is not really a ring shape, not very obviously at least. You can kind of see that there is a kind of a blob, kind of a like that, I guess, something like this, and then there's kind of little bits sticking off to the sides. And It's not typical. Let's take a look at some other planetary nebulae examples. It's kind of almost overwhelming image. Almost all of these pictures are from the Hubble Space Telescope, with a few exceptions, but you could see that they come in just a whole wide range of shapes, and the sizes, they're roughly all generally the same size physically, or at least in the same ballpark, but they're different distances, so they may appear different sizes on the sky, and from our point of view. But you can see that, like, say, for example, the Ring Nebula is the obvious ring shape on the top left. You can kind of see why Arthur Hoag thought maybe the object he saw was a planetary nebula like that, just fainter and smaller. Of course, that's not what it turned out to be, but there's lots of examples of things like that. And you can see that some of them are kind of spherical blobs with some little lines or structures. Some of them have like kind of two jets or like butterfly shapes. Some of them are just kind of bluish, kind of ripply structures. Some of them look like eyes. Lots of pretty patterns. But look how, in general, how symmetrical all of them are. That is something that kind of all have in common. They have some degree of symmetry to them. They're kind of mirrored. There may be some deviation from that, but they're generally all symmetrical. Now let's look back at our object here, and I'm gonna bring back the live view here. Um, it's sort of symmetrical, but not quite. Um, well, generally that symmetry, or especially when you have sort of a butterfly shape, is thought to be caused when you have a star that's dying that's in orbit around another star. Usually the orbits are less than a year or even on a matter of days. And when that happens, when they're kind of swirling around as they orbit each other, the material ejected from the dying star gets kind of pushed and funneled into these patterns, almost like jets emanating out from it. And it's thought that that's what's happened here too, but it has a sort of odd pattern to it, which you can see even better in this deeper image, because as that star was dying, the orbits sort of changed a little bit, or they kind of got tilted, and so the jets it was pushing off kind of sprayed out in arcs. And this is most likely a much older planetary nebula than the others, which may partly explain why it is kind of faint, and why it has so many kind of layers of structure to it. But I kind of see a jack shape to that, at least a brighter portion there. That's how I interpret it, since that's why I call it the Jack Nebula. Okay. All these nicknames are unofficial. They just stick. Um, but not a whole lot is really known about this object, NGC 6765, the Jack Nebula. Its distance isn't really known, but if we had to ballpark it, it's probably between 2,000 and 10,000 light years away, just being safe. And it's likely that this star that formed this was in the neighborhood of 3 to 5 times the mass of the sun. Again, not entirely sure. It's pretty difficult to figure out the distance to a nebula like this. It's almost impossible to do it very precisely, because it is essentially just a cloud of gas, and it's hard to get a firm idea of the bounds of it and picking a point to measure off. Usually we estimate the distance based on the white dwarf itself and how bright it is and some other characteristics, but because it's enshrouded in material, sometimes that can complicate things, and there are many other factors that come into play as well. All right, so again, that's NGC 6765. We'll take one last view at the live view in there, and you can start to see a little more of the structure coming through, and how it kind of has this sort of longer sort of tail kind of arcing off to its side there as well, roughly around there. So pretty unusual planetary nebula. Not a lot that look like that. Very few do. And that's, again, one of the objects that it's hard to find much about, because not a lot of people have looked at this, or at least intentionally observed it. Funny fact, I actually found this object completely by accident, because it was in my map in the software, and I thought I clicked on another object, and I accidentally clicked on this instead, and I slewed to it. I'm like, huh, I don't think I'm looking at the right thing, but that's interesting. But yeah, very little information out there on it. Very few people have looked into it deeply. Our next target is one of the brightest and biggest and most photogenic nebulae in the sky. It is the Swan Nebula, or M17. So again, we're going now to a highlight of the sky. And the Swan Nebula is located, let's see here, over in towards the direction of the constellation of Sagittarius, near the core of the Milky Way. So I'm going to start slewing the telescope over there, and you can see there it goes. I'm going to start moving the dome behind me as well. So you'll see the dome rotate above me. All right, almost got the dome turned around to where it needs to be. Alrighty then. So again, M17, Messier 17, the Swan Nebula. It's roughly 5,000 to 6,000 light years away, and it is not possible to see with the naked eye, but it's not far off from being able to, frankly. We're just a little brighter. You might be able to, but it is definitely possible to see in an amateur telescope with relative ease. It's something we look at a lot during our public programs in the summer here. It's just a favorite of many people who work here as well. All right, so the swan shape is going to be a bit upside down. And let me get rid of the pointer there. And I've kind of intentionally decentered it so that you can kind of see some of the area around it too, especially kind of up here. You can see that it actually extends off for a fair ways over there. But to see the swan, you can, well, we'll start with the body of the swan, which is kind of horizontal there. Let me actually do it this way. I'm gonna do it another way here. Let me get my mouse visible. There we go. All right, so here is the body of the swan. Here is its head, and it's curled down this way. So we're seeing the swan viewed in profile, upside down. There's no up and down in space. It's all arbitrary, so just use your imagination. Just rotate it around. And it's kind of like sitting on a lake in profile. So head, neck, body. And these can be seen as the wings behind it. I think that's a decent swan shape. But the swan is, in reality, a giant cloud of gas, what we call a nebula. Anything that's in space and kind of cloudy looking, regardless of how it formed or what it's doing, we call it nebula. So as I like to joke, nebula is a very nebulous term in astronomy. It applies to lots of different things. Now, the nebula we just saw before was a dying star. This is where stars are being born. Especially in the sort of brighter sections here. So there are a lot of very massive stars in here. They're very young. As these massive stars form and emit heat and energy and radiation outwards, they ionize the gas around it and make it glow. In particular, they're ionizing, or basically energizing, the hydrogen around it. And that's most of what stars are born from, are giant clouds of hydrogen, and some helium and dust and other stuff in there too, but for the most part hydrogen. And that's what's emitting the light that we see. So there's also blobs of kind of darker material, especially kind of in this region around here. Yeah, right there, you can see that there's a sort of conspicuously dark place where the gas and material is blocking the light. And so we're seeing the shadow, essentially, of this star-forming region. So again, the Swan Nebula, classic of this time of year. It does really look like a swan in a telescope. Visually, it doesn't look quite as dramatic as this. because this is a long exposure, we're stacking frames and such. But it is still really quite dramatic in an amateur telescope, and in a large telescope, visually, it's impressive too, especially impressive. All right, next up, we're going to look at another star-forming region, but one that isn't quite so well known, known as NGC, excuse me, NGC 6559. And that's our next target. It's not too far away from here. So again, we're currently looking at M17, the Swan Nebula. Next up, we're going to go to NGC 6559. Not located very far. Also in the constellation of Sagittarius and sort of the downtown portion of the Milky Way. I like to point out also in the live view of the full sky, how obvious the Milky Way is. And that is pretty close to how it looks in real life here. When you're dark adapted and you look up in the sky, that's roughly how the Milky Way looks. This field of view here is outrageously wide. It's much wider than the human eye would see, but that's about the level of sort of detail and contrast, give or take, you would see. Again, not so far from where we just looked, very close to the Swan, but a very overlooked star-forming region. It doesn't get a lot of attention, and I think that's a shame because it's not that faint. There's a lot going on in this little patch of the sky, so I think it's kind of a shame that it doesn't get a lot of attention. All right, but here is the live view. And you can see sort of a brighter patch in there, and it's going to get more obvious as we increase our exposure here, as we stack frames. So in the middle, you can see a bright star, and surrounded by a little bit of a glow. So that the bright star, actually perhaps a pair of stars, is shining light onto that cloud, and in this case, it's reflecting the light back. Not just the gas itself being energized and glowing, the gas is actually reflecting some of the starlight back, and so that's how we kind of get that nice uniform kind of glow around it. But look in the upper left corner, you can also see an almost sort of dark snake shape to it. Kind of over here, you can see that there is a dark snake-like band kind of flowing from here to there. And this is another dark nebula. We saw one in M17, but there's another here, sort of a dark material obscuring light. So it's in front of this larger kind of swath here, where there is light glowing from hydrogen again. And you can also see that there is another darker splotch here, but with a kind of a ridge to it. So you have to remember this is a three-dimensional cloud, and it's kind of sloping down and away from our perspective, and glowing a little bit, kind of on the slopes from our perspective, this kind of wall of gas. But here's another view from a larger telescope and in color, rotated around. And here you can see that there is a very obvious blue color to that around that star, and that shelf of gas is very red. And the contrast with the little river of sort of black material there is much more obvious here as well, in this much longer exposure with a larger telescope. So again, the blue is reflected light, dust and material like carbon and iron and silicon reflecting light, whereas the red is the gas itself in the cloud emitting the light. It's stimulated to do so from very energetic stars. So this is again, a star-forming region. New stars are being born in this cloud. They're only a few million years old or less. And new baby stars tend to be quite rambunctious, and they cause very pretty displays around them, as you see here, from all their heat and energy, and the kind of destroying almost sort of the neighborhoods they were born in, but also creating beautiful structures in the process, and perhaps even laying the groundwork for other stars to be born too. But this is one nebula among a very crowded portion of the sky around the core of the Milky Way, pictured here. So again, what we're just looking at is NGC 6559 on the bottom right. And it's right next to Messier 8, or the Lagoon Nebula, one of the brightest nebulae in the sky, another incredibly bright star-forming region. In fact, it is visible with the naked eye if you know where to look. It's also near M20, similar region, M17, which we looked at a minute ago, and M16, or the Eagle Nebula, which you've probably seen pictures of, such as the Pillars of Creation. But let's take one last look at the live view here, and before we wrap up for the evening, maybe just the contrast just a little bit for you. Bring in as much as we can. There we go. All right, but that's where I'm going to wrap up for this evening. Going a little bit long, but that's all right. So at this time, I'm going to take a few questions from y'all. So if you've got any questions, feel free to put them in the chat. Moderators will answer some of them, and they will also forward a few of them to me as well. All right, so Wendy Moskalik asks, do you think there is life in space with the government releasing the UFO pictures? Yeah, well, I think there is life in space. I think of all the stars you see in the sky, almost all of them have planets, and perhaps more than one, perhaps several. And there are 100 billion stars in the Milky Way, and there are trillions of galaxies in the universe, each with billions or hundreds of billions of stars, and thus hundreds of billions or even trillions of planets each. So there's a lot of places where, life could form, and even if life only forms in 0.0001% of all of those planets, that's still plenty of planets that it could form in. But I don't think they've visited Earth. I don't have an answer to what the UFO pictures are, or I have an explanation, but I don't think that there's enough information to say that it's aliens, right? We have not ruled out all of the other possibilities. There is all we know is we can't explain it right now, but there is no evidence, therefore, that it is aliens. I don't think they visited us. And I also think that the way people commonly define like intelligent life is very human-centric. Like there's lots of intelligent life on Earth aside from humans, like dolphins, elephants, uh, apes and such, that they obviously, have a firm comprehension of their surroundings. They can manipulate objects and communicate with each other, and do a lot of things that, I think qualify as intelligence, but that doesn't mean that but we still can't talk with them, and we still don't really see them as equals. And I don't know if that's really fair. I think we just sort of define intelligence around what we can do, what we're capable of. Yeah, I think there's probably life out there. It's just whether or not you find it as intelligent. That's kind of really subjective. And I don't think there's any firm evidence that it's visited us. So, all right. Stephen Nagasawa asks, I can't get light years out of my head. What's Stephen's favorite astronomy joke? This is a corny one, but my favorite astronomy joke is, um, you know, gosh, like Orion's belt, just it's only 3 stars. I can't even remember the setup now, but it's just 3 stars, right? It's anyway. It's not the greatest, but I think if I were to deliver it better, it could be better. um, Tracy Gorley asks, the nebulous hydrogen filaments are fascinating. When the camera exposure is changed, those filaments look glassy. Is that the filtered exposure of the nebula? Are those filaments multimaterial? Those filaments you're seeing, they're just very huge objects, and they look like they do because, I mean, that's kind of how they just appear in space. If you were to zoom in, they would have a little more detail, a little more fuzz to them. If you zoom in a lot and actually go there, you would basically pass right through it and never know that you're even in a nebula. The nebula is light years across, and it's just they're very diffuse. Again, you could fly right through it and never really know you're there. So the light we see is the gas itself glowing, so it is hot in a sense, but it's not really molten. But it is being sculpted by the heat and pressure from those very bright young stars. They're basically pushing material out away from them, and in some portions it's a little denser, so it resists the kind of the stellar wind coming off of it a little more. Some places it breaks away easier, but it generally it's kind of like almost like erosion on a stream, like a pebble being eroded away by the water over time. It tends to form very smooth shapes, but you can definitely get some irregular looking rocks in there too for perhaps harder rocks and such. Kind of a similar sort of dynamic going on. Um, Kimberly Guzman asks, "Do I have a favorite star?" That would be Campbell's hydrogen star. It is uh, a really faint star, but if you look at it with a big enough telescope, it has an unbelievably weird red color to it, and it's just really striking. Just visually, just striking. It was also Otto Struve's favorite star, and he was our first director here. And our first telescope was named after him, the 82-inch Otto Struve telescope. And I looked at that star with that telescope, and yeah, it was very memorable. It was just a weird kind of blood red halo around a fairly dim star. It's kind of like a planetary nebula, but not quite the same. It's very another unusual object. I actually considered looking at it tonight. It's just you kind of need a color camera to appreciate it, and it's really small. It looks better in person than it does on camera. Let's see. Kath, Kathleen asks, "Hey Stephen, what is your favorite galaxy?" That would be Hoag's object for sure, just because it's so weird. Hoag's object is such a unique galaxy in the purest sense of it. There's really nothing else quite like it, and I think that's just fascinating. There's a lot of other contenders, a lot of really pretty galaxies out there, but it really is just something else. Really stands out among the trillions of others out there. Philip Espinal asks, "What was my major in college?" I actually majored in international relations and economics. So I just took classes in physics and astronomy. But yeah, didn't actually major in astronomy. Sean CT asks, "I'm starting deep space photography. I started with the Lagoon Nebula and I'm hooked. Do you have other recommended targets that are not as common?" Not as common. Well, it depends on your skies and your telescope. If the Lagoon, you kind of mastered that, then try the Eagle Nebula M16, or even something like the Crescent Nebula NGC 6888. Those are both pretty frequently targeted, but there's also a lot of open clusters with nebulosity around them in the constellation of Cygnus that I don't think get a lot of attention by amateur astronomers. Um, there's no shortage of objects to look at in space. I mean, I wish I could fit in more targets in this program, but obviously we could be here for months, years, just going through all the different things. So, oftentimes if I'm looking for inspiration, I go to astrobin.com and just look at what other people are taking pictures of and trying to look at star charts, and maybe the star chart doesn't have a picture of something, but just find something that you haven't heard of and Google that and see if that looks kind of interesting. A lot of times, like the Jack Nebula MGC 6765, I really struggled to find many pictures of it. So I just, looked at it myself, and then after I did that, someone else actually took a better picture than me, but that's fine. That's how it works sometimes. Tie-dye astronomer asks, "What size telescope would you need to see the red color in Campbell's hydrogen star visually?" Enormous. I saw a little bit of it in our 36-inch telescope, but it didn't really pop, obviously, until I looked at it with our 82-inch or 2.1 meter telescope. It's really small, and you can kind of see the color in, the 20-inch to 30-ish inch range, but it just looks unreal in a massive telescope. Almost everything does, but it really stood out to me as something just I almost said stellar. It's a little cliche, but something something I hadn't seen before on the Autostruva 82-inch telescope. So really pretty cool. All right, well, I think that's going to wrap it up for tonight. I think, yeah, it's about all the time we have. Thank you, everybody, for joining me and all your wonderful questions and comments. We appreciate that. Also, thank you to my moderators for helping me out and making this program work and doing all the things behind the scenes that make programs like this possible. So, again, thank you, everybody. Have a good night. Clear skies, y'all.